This morning, we've heard much about Australia's ambitions in space. Mr. Ambassador, when he was Minister for Industry, did the policy work to establish the Australian Space Agency, and Harry Godber, who we met earlier, was his policy advisor. So it's only fitting that we delve more deeply into the hotbed of activity that is now happening in space. I found myself asking, with so much activity in space, how do we keep track of it all? There's now a proliferation of satellite technology and a boom of space-based activities. With this comes a rise in space debris, which in itself is an issue, before we consider the impact of the debris colliding and creating even more debris that hinders our space-based activities. So how do we predict the location of near-Earth objects? And as our ambition grows and we seek to send more spacecraft into deep space, how can we make the process more efficient? What progress are we making in having spacecraft navigate themselves, for example? And what does the level of investment in space-related research and development deliver for industry? And what's required to build the workforce to mitigate any risks and embrace the opportunities that are presented? We've invited each speaker today to consider these and other questions in short presentations before they sit down to a conversation with Harry Godber. And to our first presenter, Dr. Joseph OLeary is a research fellow with electro-optic systems who graduated from the School of Information Technology and Mathematical Sciences at the University of South Australia with a PhD in applied mathematics. Joe is a recipient of the Hamilton Prize in Applied Mathematics awarded by Sir Roger Penrose and the International Astronomical Union PhD Prize in Fundamental Astronomy. He's recently published a monograph titled General Relativistic and Post-Newtonian Dynamics for Near-Earth Objects and Solar System Bodies, which explores the important confluence between theoretical physics, applied mathematics, and space science. Welcome, Joe.
Thanks, Maria, for that lovely introduction and for the kind words. And thank you for inviting me along today to have a chat with you guys about what I've been up to for the past few years in the Australian space community and the Australian space sector. And just to tell you guys a little bit about what I'm currently doing. When I heard that Dr. Jill Shubert was going to be contributing to this session and that I had a potential opportunity to work on the same platform as Jill, I was extremely humbled. So I appreciate the opportunity, and I'm very much looking forward to an interesting Q&A afterwards. Okay, so let me kick off. So as Maria said, my name is Joe OLeary, and I work for a company called EOS Space Systems here at Lough 14 in Adelaide. I work remotely from my colleagues who are primarily Canberra-based, EOS headquarters in Symonston in the ACT. Formally, my job title is Industry Research Fellow, and I guess my area of interest is applied mathematics. I probably wouldn't be what you would consider a typical mathematician in the sense that I don't really have an interest for trying to prove the Riemann hypotheses, nor do I really have any passion for, trying to tie knots into different types of knots. And frankly, I don't have the technical capacity to do so, even if I wanted to. But my chosen area is what we call dynamical systems. And what my interest is I'm interested in trying to predict the future state of a given dynamical system. So in my role with EOS Space Systems, this system happens to be Earth orbiting spacecraft and satellites, defunct objects and space debris. And the state I'm talking about is trying to predict the future position of these objects in the system. So I thought a good place to start my presentation would be, I guess, where it started for me, at least academically speaking. If you haven't guessed by now, by my second name or by my funny accent, I'm originally from the Republic of Ireland, and in particular, I'm from Dublin. So this image I'm showing you in the background is an image taken from the International Space Station of Dublin at night time. And if you've never been to Dublin, I'd highly recommend you go there. The people are so nice, everybody is welcoming, and everybody wants to sit down and have a chat. I wouldn't go there, of course, if you wanted to get a suntan, but if you're interested in having a laugh, it's certainly a good place to visit. Now, Irish people are famous for a lot of things. The first thing is, as you know, we created Guinness, and we love having a pint of Guinness on a Friday, or at least I do, I should say. Secondly, Ireland has produced some of the world's most amazing literary figures. We've got people like George Bernard Shaw, Oscar Wilde, Brendan Behan, all of these amazing names. But what you might not know is that Ireland has a deep and rich history with subjects like applied mathematics, theoretical physics, theoretical mechanics. And I guess at this point, you're probably wondering, why on earth is this Irish guy telling me about the history of applied mathematics in Ireland? And the reason I mention it is twofold. The first is that I noticed, I was working in universities here in Australia and now working in the space sector in industry, that same sort of passion and appreciation for these classical subjects is not really as evident here in Australia as it is in Ireland. And that's something that I would really like to bring back to the Australian community, the university community, I should say. So when you're coming to the university scene in Ireland, those subjects, the opportunity to study those sort of classical subjects like classical mechanics, quantum theory, general relativity, in most applied maths undergraduate programs, you're given ample opportunity to develop those skills. And when you combine that with the tools you learn in applied mathematics, this really gives you what you need to start describing real world systems using applied mathematics. So once I finished my undergraduate degree, I met my lovely partner and we moved to Australia together. And I was a backpacker for a couple of years. And as soon as I ran out of money, I realized I probably should get a job at this point. So I started a PhD here in Adelaide at the University of South Australia. And my PhD was in a very niche area of gravitational physics, which is known as general relativity. Now, for those of you who don't know what general relativity is, I don't blame you. But for those of you that don't know what it is, general relativity is, for the purpose of this talk, an advanced theory of gravity. And it gives rise to all these kind of crazy and complicated things that you may have heard of in the news, like black holes, singularities in space-time, ripples in space-time due to cataclysmic astrophysical events, clocks which slow down, all of these things that you just wouldn't think actually happen in the real world. These are all predictions of general relativity. And my PhD looked at general relativity within the solar system, and in particular objects which are orbiting the Earth or objects which orbit the sun. And basically what I wanted to do was to spend the 2 or 3 years, trying to really understand the theoretical components. How do you describe this type of system in the framework of general relativity? Now, while my PhD was certainly academically a success, i.e. I was publishing papers and speaking at conferences and all that sort of good stuff, I was starting to realize that I really had just absolutely no idea about what you do in terms of practical applications. So for example, I didn't really understand what a sensor was. I had no idea how you then change measurements or you interact your measurements with predictions. And I really had no idea how you turn these theoretical equations that I was working with into something practical, I guess. And I guess I started to realize this when I became affiliated with the Space Environment Research Center. So the Space Environment Research Center was an Australian CRC, which was established in the early 2010, maybe around 2013. And they had the very ambitious research goal of trying to perform space debris mitigation operations using high-powered lasers. So that's really a fancy way of saying we wanted to remove space debris using photon pressure. Now, while I was affiliated with CERC, I was still going along my, I guess, academic trajectory, where I was speaking at conferences, getting applauses and claps on the back, and everyone was saying that was fantastic and it was a great presentation. But then I was also going to these kind of practical and operational conferences like this one here on the right in Amos in Maui, Hawaii, which, as you know, is just a horrible place to visit. But when I was in Maui, I was presenting the same kind of presentations, but I wasn't receiving the same kind of reception. I was getting these kind of questions like, well, what do your equations actually do? Can we monetize it? Is it better in some way than other equations? And again, I just really had no idea how to answer those questions. And I guess at this point, I started to realize, okay, I don't think I'm going to take the traditional route of an academic, which is, PhD, lectureship, professorship, whatever it may be. I thought I would take a sort of a detour into industry to learn how to build these kind of practical tools with the hope of returning to academia eventually and bringing these skills with me. So as I was finishing up my time with CERC, I was fortunate enough to get a research fellow position with EOS. And for those of you who don't know, the EOS group, or EOS, is a collection of companies which is involved in space systems and space domain awareness technologies. It's involved in defense and also communications. So I was giving a research fellow role within the astrodynamics group at EOS Space Systems. And my job now had gone from this sort of theoretical framework where I'm talking about general relativity and all these crazy things to a much more practical domain where I'm trying to describe the real environment that spacecraft are operating in, similar to the system you see in this picture. So in this picture, we can see this sort of busy beehive of activity in the center. This is actually the Earth. And these objects orbiting in that orbital regime are what we call low Earth orbiting objects. And in terms of dynamics, these objects are affected by atmospheric drag. They're affected by the fact that the Earth is not a perfect sphere. And as we move further and further away, we need to start worrying about other things. So if we look at this sort of like disk-like structure, we need to talk about this disk-like structure, by the way, is called the geobelt. And we need to worry about things like solar radiation pressure. We need to, because we're 1/10 the distance to the moon, we need to worry about the moon pulling on the spacecraft. And basically, if you like dynamical systems, this is really a dream job because you get to work in so many different orbital regimes. You get to, well, for me, I get to apply the theoretical stuff I learned in Dublin and during my PhD. And my role at EOS is then to turn this into into one of our capabilities or into one of our products. So, okay, you're probably wondering at this point, well, I mean, how many ways can you peel a potato and expect the chips to taste different? Haven't we solved this problem a million times? We know how orbits work and so on and so forth. And the answer in orbital mechanics is the chips can taste different, very different. So my role is not simply just to solve the system of equations. We know how to do this. My role is to look at the equations and figure out which part of them causes the computational burden. So I take the equations, I look at what part is slowing down the computer, and I remove that from the equations temporarily. Then I'm left with a system of equations which is computationally efficient. I solve them, and then I use some fancy algorithms to put that part back in and complete the orbit solution. Okay, I guess the last question you might ask me as well, like I was being asked at these conferences, is, well, who cares? I mean, what difference does that make? And now I kind of have an answer. I'm still working on it, but I kind of have an answer now. Well, if we were talking about the motion of one or two objects, I would say, yeah, you're right. It doesn't matter. No one should care. And, I don't care either. But when we're talking about the near Earth environment, which is becoming rapidly and densely populated with space debris, with mega constellations, and so on and so forth, that is when these kind of algorithms start to take effect and start to matter. So, right now, we're probably tracking, 20, 30,000 objects regularly. This is expected to increase to 100,000 or 200,000 objects. And in situations where, we're in time-critical situations, for example, we may expect some sort of a conjunction between objects. We need to know these predictions extremely rapidly. So I'll finish up by just saying that I think this sort of technology will really be, critical in the space domain awareness technologies going into the future. Maybe not mine in particular, but that type of algorithm is, I can really see it being, critical as we move into this sort of, I guess, space debris populated Earth environment. So I guess I'll finish there because I'm sure we're going to touch on many other topics in the Q&A. But I just want to say, I hope you enjoy the rest of your work summit, and thank you for listening to me today.
Thanks so much, Joe. I'm still trying to get my head around the fact that there'll be so many objects in orbit. I don't know how we manage to do it. We introduce complexity wherever we go. Now to Dr. Jill Shubert. Jill's an interplanetary navigator and a leading expert on astrodynamics, estimation theory, and technology advancements to support the next generation of deep space exploration. In her 10 years as a navigator at NASA's Jet Propulsion Laboratory, she has navigated numerous high-profile NASA Mars missions, including the Mars Reconnaissance Orbiter and the InSight lander. She most recently served as the Orbit Determination Lead for the Perseverance rover, guiding it to safe landing on Mars on February 18, 2021. Dr. Shubert was also the Deputy Principal Investigator and Mission Operations Manager of NASA's successful Deep Space Atomic Clock Technology Demonstration Mission. She now lives in Sydney and is the founder of Australis Space Navigation. Jill was awarded the 2020 NASA Exceptional Public Achievement Medal for her outstanding leadership of the Deep Space Atomic Clock mission. She's been honoured as the recipient of the University of Colorado College of Engineering Recent Alumni Award in 2017 and the inaugural Penn State 40 Under 40 Award in 2021. Jill holds a Bachelor of Science degree in Aerospace Engineering from Pennsylvania State University and Master of Science and PhD degrees in Aerospace Engineering Sciences from the University of Colorado at Boulder. Welcome, Jill. It's an honor to have you.
Great. Thanks, Maria. Thanks for such a kind and warming welcome and introduction there. Let me just start by echoing Joe's sentiments. I am so honored to be part of today's panel. I'm just thrilled to be considered high enough in my field to even be talking with all of you in this panel today. So as Maria said, I am Dr. Jill Shubert, and I am an interplanetary navigator. And before we get into what that actually means, because yes, that is a real job title, first I'll just give you a really quick history of who I am. Now, as you probably guessed from my bio and from the fact that I will pronounce some of my words a little differently than Maria just did in my introduction, I'm a US citizen. I was born and raised in Pennsylvania. I've had a history of moving around the United States. I lived in Maui. I actually worked at the US Air Force Research Labs and went to that wonderful Amos conference where Joe got up there and realized that he didn't understand anything about his field. And ironically, that's also the conference where I realized I didn't know anything about my field. But we can always get into that in the Q&A if there's time later. So I worked at the Air Force working in space situational awareness, like what Joe is supporting now. And then after I finished working there, I actually went back to school and I went to the University of Colorado at Boulder, where I got my, as Maria said, my master's and my PhDs in aerospace engineering sciences. And, you know, perhaps most importantly there, I also met another aerospace engineer who was an Australian citizen, is an Australian citizen. We got married some years later, and that indirectly led me to my path here. So the last 10 years prior to moving, and I should actually say we moved about 6 months ago, 6 months today, actually, we moved to Australia. So I am pretty new to Australian soil here and still getting my footing here. And the last 10 years before that, I spent navigating spacecraft at NASA's Jet Propulsion Laboratory. And I worked on some Earth missions and a lot of Mars missions. And most recently, I was the Orbit Determination Lead for the Mars 2020, or the Mars Perseverance rover, as it was known more colloquially. And that's actually an artist's image that you see here on my slide. This is one of my favorite images. It's capturing what it might look like as Perseverance was screaming down into the atmosphere of Mars and about to eject that back shell and parachute land that rover down safely on the surface of Mars. And yeah, that was just about 1 year ago that we landed it there. So as you can see, I'm still on a high from landing that rover. And I think that will always be in my blood. Being an interplanetary navigator is part of my DNA. It's very much who I am. And while I'm pretty new to Australia, I also very recently founded my own company, Australis Space Navigation, to allow me to continue providing my interplanetary navigation skills on a consulting basis. So since I'm willing to bet that I am the first interplanetary navigator that most people who are watching today have actually met, Let me just explain my job to you a little bit. And as I said, it is a real job, because some people, when they hear that, they kind of, their eyes glaze over and they look at me like, she is clearly making this up. That's something that sounds like it's on Star Trek or Star Wars or something. But basically, an interplanetary navigator is, we're responsible for guiding spacecraft throughout the solar system, from the moment they separate from the launch vehicle to whenever they get to their final destinations. Now, that could be giving directions to get the spacecraft along its very short 7-month cruise from Earth to Mars, or it could be, say, spending 17 years guiding a spacecraft as it tours Saturn and the various moons in the Saturnian system. And navigation is kind of like this connective tissue across an entire space mission. We start working on it back in the design phase, and it leads us to make decisions about things like how much fuel do we need to carry on board. And that may have further down the line repercussions on what science instruments you can actually carry. And then we also support the missions all the way through launch, through cruise, and then landing operations, or perhaps going into orbit around a foreign body. Now, there's really 2 parts to the navigator's job. The first is to determine where the spacecraft has been in the past, and then we use that information, as well as our models of the spacecraft and the solar system, to predict where the spacecraft is going. And we want to know, where is it going to be at a very specific time. And then most importantly, we attempt to quantify how well or how little we actually know any of this. And this is all in the end here so that we can deliver this information to the spacecraft operations team that we are part of. And then the operations team can make informed decisions, like, are we on the right path and we just stay the course, or are we going to miss our target and crash into Mars, and we better fire our thrusters to make sure that we don't do that. Now, this might not seem all that hard. I mean, after all, I can pick up my cell phone, I can open up Google Maps, and it does a really good job of showing me with that little blue dot exactly where I am. It'll know where I am sitting in Sydney right now. But it's a little bit trickier when we're out in deep space, because there's no GPS system there. There's no GPS to guide us. There's a lot of unpredictable things that can actually happen in space, believe it or not. And this is remote operations at its very most remote. We're talking about things that are so far away that you cannot measure anything truly directly. And all of the real-time data that we're working with is telling us what actually happened at least 20 minutes ago, sometimes hours ago at this point. And timing is absolutely everything for deep space navigation. We can't actually measure how far a spacecraft is, how far away it is from us. So in order to figure out where a spacecraft is, we actually just measure how long it takes for us to send a radio signal from Earth to the spacecraft and back again. And then, since radio signals travel at the speed of light, we can back out how far away the spacecraft is, and looking at the change in that over time, we can figure out the velocity of the spacecraft, or measure the velocity of the spacecraft, I should say. And right now we have to do it that way because the only clocks that are good enough to actually take that measurement are about the size of a refrigerator. So that's actually bigger than many of the spacecraft that we're able to send out into deep space. But that is changing, and we'll talk about that a little bit later on. Now, just to wrap up the little bit of background about interplanetary navigators, there are 2 really important days in a navigator's life on a mission, and that is launch day and landing day. Now, predicting the trajectory correctly after the spacecraft separates from the launch vehicle is very important, because it means we know where we need to point those ground antennas so that we do not lose the ability to communicate with spacecraft. The main goal on launch day is do not lose the spacecraft in space. And then on landing day, our main job is predicting when, where, and at what incoming angle the spacecraft is going to enter the Martian atmosphere. And it's actually critical for landing the spacecraft safely. We tend to make it look pretty easy, I think, when you watch it on TV and you're watching NASA's mission control. But there's actually a very narrow window of opportunity between just flying right past Mars or coming in at a very steep angle and crashing catastrophically into the surface and creating a new crater, or coming in at just the right angle that whole autonomous landing system works perfectly and we can land our spacecraft safely. Because don't forget, these spacecrafts that we're trying to land, they're like the size of an SUV, so they're a little bit heavy to get down to the surface. And to do it properly, the navigator's job is like shooting an arrow from Adelaide and actually hitting the bullseye of a target that's sitting in Perth. And if I'm going to be honest with all of you, which I always will be, it's a really, really fun job. And that's why I'm so psyched that I get to continue doing it here. So here is a recent photo of JPL's spaceflight operations facility. This is where we actually do our deep space navigation at JPL, the Jet Propulsion Laboratory. And I just wanted to quickly talk about what kind of skills are important if you want to get into this room. Many people have asked me over the years, how do I get your job? I once asked someone that question, how do I get your job? And so I just like to advertise what you need in order to get this job. And I'll say this is only my opinion. There's no official list out there somewhere, but I've been fairly successful with this, so I'd like to share it. And I like to break the skills down into two categories. There's your technical skills, your knowledge, and then there's also your personal character or your soft skills. And the good news is that all of these things can be learned. I don't think anyone's born with this magic set of skills. Now, it goes without saying that for various specialties in spacecraft navigation, the technical expertise is very important. For navigation, it's primarily a lot of the things that Joe was actually saying: astrodynamics, estimation theory, knowing how to model your measurement system and space weather, knowing how to model your gravity system that you're modeling, knowing about the relevant spacecraft subsystems like propulsion or attitude control, and very importantly, knowing the best and worst case scenarios that the industry can actually deliver you. How well can those sensors and those actuators really work? And then I also want to point out that while I have a PhD is not strictly necessary to have my job. I have worked with some absolutely stellar navigators out there who have had master's degrees or bachelor's degrees. I would say that 99% of the important information in my job was on the job training, actually. Now, another skill that's really important is the development and execution of effective training programs. And I really can't emphasize that enough, because you really need to train the entire team so that a mission can be smoothly carried out when everything goes as planned, but perhaps more importantly, to make sure that your team is prepared to snap into action and work efficiently and effectively on those bad days when bad things happen. And believe it or not, bad things happen quite often in space missions. We're just trained to deal with them and make them look very smooth. But we actually need to execute these full-scale rehearsals and prove that we can pass the test. We have the muster to land on Mars on a bad day or a good day. And we need to make sure that we can demonstrate that before we're even given approval to launch these spacecraft. So before they're even off the ground, we have to prove that we can do the job. So knowing how to actually craft a training program that will demonstrate all that is a really critical skill. And it's something that you really just gain through experience, I've found. But I'll also say, speaking of experience, it's actually the soft skills that I think are more important. Things like the flexibility to adapt when the situation changes rapidly, or to perform in a very stressful situation. Effective team leadership and understanding very complex personal dynamics is a very important skill. Being well organized, and I would say keeping perspective on why the 1 million little things that you have modeled in your system actually matter to the spacecraft team during operations. And then I would say most importantly, and I think you hear this across the board, you need to know how to communicate. To pull something off, like landing an SUV on Mars, you need to know how to talk to people, how to communicate the important parts when something is going right or something is going wrong. And, I always like to bring up one of the greatest failures that the world knows about with deep space exploration. And this was the Mars Climate Observer. We sometimes refer to it as he who shall not be named in my profession, but it was the Mars Climate Observer, and it smashed into the backside of Mars in 1999. And that was the end of the mission, got it all the way there, and then it crash landed. And this is the one that's most famously known as being due to a units conversion error. One team was working in imperial units and the other team was working in metric units. And I will say that an investigation, post-mortem investigation, revealed that at the end of the day, it didn't matter who was working in what units. It was actually a failure to communicate between all the various teams that led to the massive failure of that mission. Now, there's one skill that I actually don't think should be required in order to be in this room, and that is physically being in the room. As you can see, the room in this picture is pretty empty. And believe it or not, this photo was taken in the final moments before we landed Perseverance on Mars. So normally when you see that on TV, you see the room is packed wall to wall with people, everybody's wearing the same polo shirts and we're all jazzed up and then cheering and attempting to high five at such. But this mission, Perseverance, happened entirely during the COVID pandemic. And that leads to my last couple of points, which is where I think interplanetary navigation should be headed and how we should be changing things. So COVID-19, let's talk about that quickly first. It taught us that there's no need to actually be in mission control to land on Mars. And for the history of space exploration, mission control has looked just like what you see in the movies, like in Apollo 13. It's a big room full of computer consoles. The engineers are in their white shirts and they're hunched over their computers, reading out telemetry over their headsets, and it's all very intense. But the COVID-19 pandemic didn't allow that to happen for Perseverance. The pandemic started shortly before Perseverance was set to launch, and NASA had a choice between delay the launch until ? When things are safe enough to do this in person, or we attempt to do this remotely with everyone on the team working from their home offices. So they obviously chose the latter. And with the exception of a few on-site team members in case a spacecraft anomaly occurred, we did the entire mission from our home offices. And so we are living proof that we can actually succeed in doing this. And so I think that virtual mission control, or at least the option to do this for certain critical time periods, will create opportunities for talented individuals who don't want to be limited by the constraints of living in the very few geographical locations where we actually have mission controls. Places like Pasadena or Houston. You have people like me who no longer want to live in those areas, and they can move to wherever their families are, to wherever they want to have a better quality of living, and still contribute their very special skills to these very special missions. And I think that this is going to do a few things. It's going to allow us to reduce mission risk by no longer having very tired navigators working 24/7, because that is where the mistakes happen when you're working your third shift. And it's also going to reduce all of that bickering between the nav team when you have to fight over who has to actually work that third shift. I will be honest, and virtual navigation will require another level of communication and transparency. And there are issues that we have to address, primarily internet connections, but I think it's been proven to work. And I think we need to go there in the future. And the reason we need to go there is because hopefully not all that far off from now, having a dedicated mission control at all might not really matter. It might all be a moot point, because I think it's time that we commit to advancing autonomous spacecraft navigation, and we just let the spacecraft navigate themselves. We call autonomous interplanetary navigation, we call it AutoNav for short. And it's still not here. Self-driving cars are no longer work of fiction. They're here in some capability, but AutoNav for spacecraft is just nowhere near actual deployment. Now, there have been a few demos, 2 demos to speak of, Deep Space One and Deep Impact, but those were both back in the 1990s, so it's been a while since we took a look at this technology. And as more spacecraft are launched, the tracking networks and the navigators and the people like me, we are all resources, and we're being stretched very, very thin by having to take care of navigating all of those spacecraft and tracking all of those spacecraft. And honestly, we're getting rather close. The whole system is getting rather close to saturation. So letting the spacecraft navigate themselves would actually just relieve a lot of system pressure. And it would also add some safety to our spacecraft missions, especially when you have a crew on board, because not having the spacecraft able to navigate itself on board, but having to rely on directions that are being sent from Earth, it puts another level of risk onto those spacecraft where you cannot react fast enough to something going wrong, and you could end your mission catastrophically. The really great news is that we've taken one huge step towards making autonomous interplanetary navigation a reality, and that is that in 2019, we demoed a very accurate, very stable space clock, the Deep Space Atomic Clock, which is just as good as those refrigerator-sized clocks that we needed to measure time before. So with that, we can then measure time directly on the spacecraft, collect those measurements on the spacecraft, let the onboard computer chunk out the navigation system, and essentially do my job for me so that I can be out of work someday. Now, this clock technology has flown in Earth orbit. Very soon, we should be seeing it go further out into the solar system. So I'm hopeful that this gets some traction in the next decade, and it's plausible that this could actually become more mainstream in my actual career. But it is going to be a very large-scale commitment. It's going to be leading us to accept some level of risk in our future missions. And it also takes a good hard look at where we are now and where we want to be in deep space exploration in the future. So with that, that's really where I'll wrap up with there. And I look forward to having some good conversation with Harry and Joe about all of this. Thank you.
Absolutely. Thank you so much, Jill and Joe. It's really thrilling to have two professionals who are at the apex of their disciplines. Unsurprisingly, this session is one of the more popular ones when it comes to subscriber comments, delegate questions. And we'll get to some of those in a moment, but I have one or two of my own that I would like to put to you. As Maria mentioned, I worked with Ambassador Sinodinos when he was Minister for Industry, helping set up the space agency in Australia. We were one of the later countries to adopt a space agency, but I think the work that they've done since has more than made up for the time delay. And one of the reasons why that agency was created was to foster collaboration between industry and academia and between different nations in space missions and space research. So I might go to you first, Joe, because you really work at the fulcrum of industry and academia in this space, having been at CERC and having now been at EOS for some time. What are the factors that you feel hold us back when it comes to industry and academia collaborating in the space industry?
Oh, that is a good question. I think it's a good question, and I think that in the space community, if you study orbital mechanics as an academic and you study orbital mechanics in industry, they're almost two different fields. Basically, we want different things. So, for example, in academia, you may study orbital mechanics long term. You might want to uncover what type of effect does this resonant behavior have? Does my system exhibit chaos or something like this over 2 decades or 5 decades? People in the industry are not interested in those problems. We're talking about different time scales, 30 seconds, 5 minutes, days. And I guess, to answer your question, I suppose, well, they're very different, but there's no reason that they shouldn't be able to coalesce eventually. I think places like the SmartSat, places like CERC, as you've mentioned, and the Australian Space Agency are trying their best to bring projects together, to put projects out there which bring the best from both academics, so they can work on theoretical ideas, and then they can get the advice from the industry experts about how you make that into something practical. And I guess, as you said, that's something that I'm doing now. I'm still trying to figure it out, really. It's a complicated problem. But yeah, I guess that's what I would have to say on it, I suppose.
That's really interesting. And I think, Jill, you've spoken about communication of research in this space and its consequences in the past. Could you perhaps describe how critical the work that you do is to things that we use every day, and what are the risks that we would face with current levels of collaboration and resourcing and global interest in space navigation?
So I don't know how important the things I do on every single day are important to your daily lives out there. But, historically, if you take a look at, let's just talk things that we have obtained as a byproduct of space research and space exploration, things in our everyday lives, like Velcro. Velcro came from a need to attach things to the ISS. Or not the ISS, Apollo missions, excuse me. Things like digital cameras came about because we needed them for deep space missions. They actually came from the Jet Propulsion Laboratory originally. The GPS system that we all use in our phones every day. A lot of this is a byproduct that was not the intended reason why we created these space research endeavors, but they end up streaming and trickling down to users all around the world. I think one of the risks with that is we take a lot of it for granted. I think we don't think about, where did GPS come from? What was it originally for? What was a ballpoint pen originally for? And when we think about these things, we are, as a layperson, unable to really connect our everyday lives and things that are important to us with what seems like very far off lofty goals, and some people would consider a waste of money, really, sending spacecraft into deep space. Why are we sending a robot to Mars to dig around and figure out if there was ever water there? What are we getting from that? And so you risk having people not support those missions. And I think we need to do a very good job of communicating why it is important that we're doing these things so that we can get that support. But then there's also all these intangible things that we get as this great byproduct of what we do with deep space exploration, or really any space research and exploration. And that's getting really smart people excited to work in the STEM fields. And I think that you cannot possibly quantify what you're getting when you get a really smart person excited about what you're doing. And I have worked with many students that are so bright and they show so much potential, and they might not at the end of the day choose to do what I do, and that is perfectly fine. They choose to find their own path, but they learn how to ask questions, and they learn how to think about not just accepting what we have, but actually creating a better future. And that is what the real payoff is for us. So I think really trying to just think about those intangible things that we're getting really brings it to light for me. Why are we doing these things that we do?
That global collective interest is a really interesting point. I mean, you obviously work, Jill, with a variety of clients across different nations and alliances. How diplomatically complex is space right now? Is everyone in it together? Is there still more work to do?
Yeah, I think that the real answer is probably above my pay grade, but it is both collaborative and contentious, I would say. There is still a lot of competition for the various things that we're trying to do in space, both politically and then also just geometrically. Things like landing on Mars. We have a very finite window in which we can launch something from Earth and actually land on an interesting spot on Mars. You have to do it in this certain, say, 1 month time frame. That's when you have to leave Earth, or you have to wait another 2 years to do it, at least another 2 years to do it. And so what we find is that we have across the globe, the US, Australia, there are many countries out there that are actually interested in sending probes out into deep space. And when you're all trying to launch and follow essentially the same path at the same time, you can envision it like a crowded highway. It's like if everyone gets off work and leaves at the same time and tries to head to the same vacation spot, the roads are going to get packed. The gas stations are going to get packed as well. For us, for spacecraft, it's the tracking networks. They just get saturated trying to track those spacecraft. The navigators get saturated. The spacecraft teams are looking at too many different things. And so there's a need to really collaborate globally. Instead of having all of that competition for let's say, smaller missions, we can collaborate more, put our resources together on the same spacecraft, really optimize what we're trying to do, not compete with each other. And I think we'd be able to push our exploration a little bit further if we were able to figure out a way to do that. And we are doing that on I was about to say we're doing it on a small scale, but it's really quite a large scale at the Mars Science Return mission, which it's a global international conglomerate here that's going to be happening later this decade to send another 2 spacecraft out to Mars and collect some samples from the surface, bring them back to the Earth. So for the very first time, we could actually analyze them in our very highly advanced labs here on Earth.
Absolutely. And I'm going to come to your Mars endeavors shortly. But Joe, I think it would be remiss of me not to bring up the Ukraine situation in this session, because it's certainly on the minds of everybody. And about a week ago, I think Elon Musk activated Starlink satellites to give Ukraine internet data backup. What sort of things would the Starlink planners have had to consider before they released those satellites? What's the margin for error in an activity like this?
That's a good question. And look, the Starlink spacecraft are orbiting in Leo with a particular inclination, maybe 53 degrees or 54 degrees relative to the equator. And there's about 14 or 1500 spacecraft. So I don't think the issue would have been coverage, because for relatively low latitude countries, like up to 60 degrees latitude in the northern hemisphere, SpaceLink will have completely Starlink, SpaceLink is the EOS company. Starlink would have global coverage, so to speak. So I'm not sure if I could be wrong, but I'm not sure if this question is really an orbital mechanics question, but rather a telecommunications issue. However, I think what you are asking about is sort of orbital maneuvers. And so orbital maneuvers happen all the time. If we look at objects out at GEO, GEO is a very special part of the orbital regimes. And GEO is typically, reserved for communication satellites, navigation, spacecraft, and so on. But GEO satellites drift. They have longitudinal drift, and they move out of place. And they need to be maneuvered quite frequently to perform, which is what's called station keeping activities, so that they maintain communication links with some receivers here on Earth. Again, coming down closer to Earth, as in LEO regions, maneuvers again happen all the time. For example, the International Space Station has to perform, regular, altitude raising maneuvers because it's affected by drag. And again, in LEO, objects, it's quite a busy kind of beehive area, and I'm not sure how often they have to maneuver, but I'm imagining it's quite often. It's in astrodynamics, as Jill will, I'm sure, agree. There's no one number I can tell you as a margin for error. Like if you asked anyone at EOS, you would say, how well can you track objects? I would respond by saying, it depends on the object, So, so I'll probably disappoint you in that sense, but I can't quantify in saying what kind of margin for error there is. But I mean, for when you are performing these kind of maneuvers in LEO, you would have to have, kind of great knowledge of what's happening around your objects, so to speak.
Absolutely. And I think, space junk is certainly a mounting issue, as you both alluded to. In your time at the Space Environment Research Centre, that was certainly a focus and something that Australia has been a leader in. Tell us a bit about some of that work and, how Australia is leading the way in helping rid space of junk. And I think we also recently saw China essentially fling a spacecraft out of orbit. Is that right? How far is that going to go?
Yeah, well, let me start off with the Chinese debris mitigation operation. So the spacecraft that did that was called SJ-21, S for Sierra, J for Juliet, and 21 for the legal drinking age in America. So SJ-21 was this really interesting experimental debris mitigation spacecraft launched by China. And that was orbiting at GEO, and basically it was doing some RPO, which is rendezvous and proximity operations around an old Chinese navigation spacecraft. And most companies around the world that are interested in space data or who have some type of SDA sensor would have been tracking this RPO on some level. And so basically what it did was, as you said, it docked with the navigation spacecraft and essentially took it out of the GEO belt and launched it into a graveyard orbit. And I mean, what an amazing feat of engineering. And I'm sure their astrodynamics team is, pretty ecstatic. But coming back to Australia, yes, Australia, the CERC program was involved with coming up with some nice debris mitigation strategies. And as I said before, the idea was to essentially use a very high-powered laser to move a piece of debris out of its orbit and to burn up in the atmosphere. Being a CRC, it is a research organization, and the experiment hasn't been performed, but it is a step in the right direction. I mean, it's demonstrating all the things that we need to. It did all of the correct research, and this experiment may happen again, or may happen in the future with EOS space systems. But it is a great indication that we're on the right path, because you must remember, 2 or 3 or 4 years ago, the idea, or 5 years ago maybe, the idea of removing space debris was simply something you would just hear at an academic conference. Now it's actually happening. So while the CERC program actually did not do the maneuver, I do believe it will happen in the future. So all of these things are great steps for, trying to reduce, or at least trying to prolong our, space environment and keep it as sustainable as possible.
Absolutely. Thank you, Joe. Jill, I've really got to ask you about your Mars work. I think it's fair to say you've operated at the apex of working from home, as well as the apex of your profession. For those of us who aren't experts in the field, give us a bit of a picture of what's involved when you're navigating a spacecraft between launch and return. I'm sure that some in the room would be picturing you sitting with a joystick at a computer like the drone pilot, but how does it actually work?
Well, first, let me say that I think I did reach the apex of working from home, because I landed I shouldn't say I landed, because the whole team landed, right? Our team landed, but my contribution was done while I was sitting in front of my computer at home with 2 toddlers literally climbing on me as I'm trying to like swat their hands away from the keyboard so they can't actually punch in anything that could do harm in the last few moments of the mission. So that's another mission risk I should have mentioned. Having children and you're working from home is a very high mission risk. But Harry, to answer your question, no, it's not quite as like visually exciting as me sitting here with a joystick, like I'm using a 1980s computer game or something and navigating the thing. Although that we do have VR headsets that they use sometimes for the surface operations, so that you can virtually see, if you were the rover, you can see what would be in front of you when you're on the spacecraft. You could see obstacles that you would need to steer around and such. They're experimental, but I imagine they'd be using them soon. But for me, what my job is really writing computer programs, knowing how to test those computer programs, and then using them in operation. So it's a lot of programming, which I know sounds really, really boring to many people. But, you know, talking about all the ones and zeros and putting it all together, but it's the testing and the application where the exciting part comes in. And so for me, for operations, for many, many years before the spacecraft launches, you're writing these scripts, you're developing tools, you're testing them using simulated data. And then after the spacecraft launches, we then collect data from the Deep Space Network, which is a series of ground telescopes. The largest ones are 70 meters in diameter. They're absolutely huge. They can connect with the spacecraft no matter where it is in the solar system. You always have visibility from at least one of these big antennas. One of them is in Canberra, very close to our hearts here. And we collect radio signals from these big antennas. They get routed through the Deep Space Network system to essentially my computer. And I then look at that data and I can compare what I thought it should look like versus what it does look like. And in looking at these visual differences, we call them measurement residuals between what we thought we'd see and what we do see. We try to back out anything that is unexpected. Obviously, you want it to look exactly like what you were predicting it to look like. You want to see, let's say, numerically zeros across the board. That is never going to be the case, because these radio signals, they're traveling sometimes millions of miles to get from one end of the signal to the other. And it'll be passing through a lot of plasma through space. The sun could have let out a big burp of gas in just the wrong direction. And so you're seeing that signature in the residuals that you're looking at. Or say you could have a blizzard in Madrid and the snow is mucking with your signal and you're trying to figure out, am I looking at the effects of a snow blizzard shaking my antenna around, or am I looking at the effects of the spacecraft maybe having a leak in its gas tank and it's slowly going off course? Obviously, one of those things you're going to be worried about much more than the other. So it's statistically looking at the difference between reality and, or I should say, it's the difference between looking at measurements and then looking at what reality you think best fits those measurements, and trying to minimize the difference between those two so that you can then accurately predict where the spacecraft is going. And so every single day we are always looking at, well, I predicted the spacecraft was going to be there, but it looks like it's actually over here. So my prediction was wrong. And so we're constantly updating that as we get new information. So it's not quite to the level of actually steering the thing with a joystick, but then once I determine whether or not we're on the correct path, I can let the propulsion team know that. The maneuver design team can figure out how to get us back to that target I was originally trying to get us on. The propulsion team fires the engines to make that happen. And then I again look at it and say, okay, yep, you got it. We're back on track. Or, oops, that wasn't quite what we meant to do. I think we need to do something else to get us there. Hopefully that makes sense, Harry.
Absolutely, it does. And it's fascinating. I reckon that most people who are studying in any of the fields that you've mentioned at university or thinking about it often wouldn't contemplate coming into the space industry. And I know, Joe, you've mentioned to me that when you were undertaking your studies, it certainly wasn't something that you were really thinking of. Joe, what sort of skills do you want to see entering the market to exploit all the opportunities that are available? And are there any policies or plans with regard to skills that you really want to see policymakers and business leaders contemplating?
That's a good question, and I can only really answer for what, like, my kind of area, I suppose. I mean, this shouldn't be taken to be, what I think would change the whole space sector. But what I would like to see is more young people coming through who are classically trained in mathematics, as in they know how to solve differential equations. They know Hamiltonian mechanics. They know mechanics basically, so they know how to use mathematics to describe systems. To describe physical systems, I should say. And the reason I think that's important is because if you look back to the dawn of the space age, around the 1960s, 1970s, the US were just doing absolutely amazing things in terms of analytical mechanics. So they had academics solving these equations, and the mathematics that they were doing was not particularly super advanced in any way. Undergraduates could probably learn it. But they were just doing amazing things. And these equations that they published, the Americans at the time, were turned into some orbital prediction models that we still use today. And the US have only recently gone ahead and upgraded those models to be slightly better dynamically, to basically so that we can explore cislunar space. Now, I think Australia has a great opportunity to be building, we don't want to be building the same thing because, that's just a waste of time. But we have an opportunity to build our own sovereign capabilities by training young people in these areas. And I think I've got a few ways to do that. But basically, I would like to see more people coming through who are formally trained in mathematics. While I understand that, it's very important that you know how to run software and build software, what I think is also super important is that the students know what the equations actually do. So when something breaks, they don't just say, oh, well, my debugger says it's line 15. I say, well, no, let's just take out a pen and paper. Are the dimensions correct? Something like this. So that's kind of what I would like to see. Well, I guess that's what I would like to see. Yeah.
That's really interesting and definitely food for thought for the educators in the audience. On the topic of sort of business and policymakers and the plans they might be contemplating, Jill, I want to finish on a question close to my heart, which is government funding for space activity. You've described how revolutionary the Deep Space Atomic Clock is going to be. That mission cost NASA $80 million, I think, which in the grand scheme of things seems like a pretty small price to pay to secure an answer to a problem that's going to unlock enormous productivity. But for policymakers day to day, when they're pitching space funding against funding for things that might seem closer to the everyday voter's heart, it can be a difficult decision. How would you express these decisions and what space funding can unlock for us?
Yeah, and the Deep Space Atomic Clock, I want to say the final number was $82 million. So very good. You've done your research in that. And I think that it comes down to, it's not a dollar's cost that always matters. So yes, that mission was relatively cheap in the scale of government funding, especially American government funding of space missions. $82 million is really just a drop in that bucket, much as sometimes it pains us to say these kinds of things. And we did some fantastic work with that little money. We demonstrated the world's most stable space clock. It was quite a fantastic feat that we were able to do that with $82 million. But what tends to hold up technology that really pushes the limits, like this Deep Space Atomic Clock, is not the dollar's cost. It's not however many pennies went into that bucket, but actually the cost as far as what is the risk that a project or a spacecraft team is willing to accept. With every new technology, there's always going to be a little bit of risk that you need to accept if you're going to ever adopt that. There are ways to mitigate it so that you can test new technologies, you can start incorporating these new things as your mission baseline without actually putting the mission at risk. But it's really a change in a mindset in order to get a government agency to really realize we need to embrace risk instead of just shying away from it. I mentioned a massive failure that we had before when we crashed the Mars Climate Observer into Mars. Everybody remembers all the times that you screw it up. We don't always focus on all the times that you got it right. We're scared of risk. We're scared to actually take those steps. But if we're going to be scared of risk, we're never, as a government agency, as a people, whoever we are never going to be able to really push our limits and move forward. And then there's also another thing that holds technology back, and that is, with every piece of technology that you choose to fly on a spacecraft, you have to leave something else off the spacecraft. Right now, with the limits that we have, until we can launch an infinite mass into space, everything weighs something. And the more your spacecraft weighs, the more fuel it takes, the more launch power you need to get off that launch pad. So you make a decision to fly an atomic clock, you're making essentially the decision to take a science instrument off. So it's always pros and cons of what you want to fly. And so what we need to focus on is making things small, making sure we don't have any too redundant systems, too much redundancy in our systems, so that we're flying things that we don't need to fly, in order to, going full circle, make sure that we can still mitigate the risk on those systems and fly what we need to fly, while also taking on board some new things and demonstrating it. Now, one thing, I'll just wrap up by saying one thing that NASA did that's quite clever is they have a directorate that is dedicated to flying in space new technologies. So when a project doesn't want to take on a new space technology because it might be too risky, there is a whole division that says, okay, that's our job. We will test this new technology. We will get it to a level where other projects, other missions are more comfortable adopting it. The Deep Space Atomic Clock was a true success story of going with that paradigm. And now, having shown that that technology is successful, pretty soon it's going to be flying onto Venus with the Veritas mission, and hopefully it will get some traction in the upcoming Artemis missions as well. So there are ways in which government agencies can in fact direct their funding to push to new technologies, exactly like we've done with the atomic clock.
Well, Jill, I think entrepreneurial and risk-embracing decision-making on the part of policymakers and industry and academia, indeed, is certainly a theme that's resonating today. Jill Shubert, Joe OLeary, thank you so much for joining us. It's been a real privilege to hear your take on the future of space and the space industry and the skills and resources that are going to be required. Thank you for joining us today.
Great. Thank you, Harry. Thank you, Joe.
Cheers. Thanks, guys.